Hello, today's learning objective is about electrophilic substitution reactions of benzene. Benzene, it is rich source of pi electrons which can easily be shed. So, both the alkenes, benzene are susceptible for the electrophilic attack and both form the carbonium ions as an intermediate. See, explaining in detail, let me give some introduction about electrophilic substitutions. What is a substitution reaction? Substitution reaction in organic chemistry. It is a reaction in which a weaker atom or a group is substituted by a stronger atom or a group. Is called substitution reaction. These substitution reactions are of three types. Substitution reactions are of three types: electrophilic, nucleophilic, and free radical substitutions. Electrophilic, nucleophilic, and free radical substitutions. Nucleophilic substitution reactions you can observe in alkyl halides, the halogen compounds we can see. What is a nucleophilic substitution? The substitution of a weaker nucleophile by a stronger nucleophile. It can be the nucleophile is the negatively charged species. Nucleophile is the negatively charged species. And coming to the electrophile is the positively charged species. The reagents are of three types. As we all know, the reagents are of three types: electrophile, nucleophile, and free radical. So in the types of reactions, this substitution reactions, three types: electrophilic substitutions. In the electrophilic substitutions, a positive nucleophile or atom is replaced by a stronger stronger electrophile atom or group. Is called electrophilic substitution. Now, what is free radical substitution? As you know, electrophile, it is a positively charged species. The reagent is positively charged species. Nucleophile is negatively charged species. What about the free radical? Free radical, it is not having any charge. So if a weaker free radical is substituted by stronger nucleophile, then that is free radical substitution reaction. Now, we can observe free radical substitutions in alkanes. And nucleophilic substitutions can be methane halogenation, methane chlorination are the free radical substitutions. And the substitution displacement reaction, the nucleophilic substitutions are observed in alkyl halides. And the substitution displacement electrophilic takes place in the benzene. The replacement of an atom or a group from a molecule by different atom or a group is called substitution, I've discussed. So free radical substitutions in which free radicals are formed as intermediates, and the weaker radical is replaced by a stronger radical is free radical substitution. And coming to the nucleophilic substitution, as I have told you, the substitution reactions which involve attack of nucleophile is nothing but a nucleophilic substitution. You have SN1, SN2, and it takes place in alkyl halides. Now comes our actual topic, that is electrophilic substitutions. The third type of substitution reactions is electrophilic substitution reactions. Electrophilic substitutions are the substitutions which involve the attack of an electrophile. Generally, SE you call. S stands for substitution, E stands for electrophile, and these are common in aromatic compounds. Electrophilic substitutions are common in aromatic compounds. Example: nitration, halogenation, sulfonation, Friedel-Crafts reaction, alkylation. All these come under the electrophilic substitutions. So today's objective is I'm going to discuss in detail about the nitration and sulfonation. Nitration and sulfonation, we'll see. See, first, benzene. Coming to the benzene, it is a rich source of benzene. It is a rich source of the pi electrons. These can be easily shared. These can be easily shared. The pi electrons of the benzene can be easily shared. Benzene forms a monosubstituted compounds. Nitrobenzene, when all the hydrogens can be replaced. Aromatic hydrocarbons have general formula CN H2n minus 6, where n is greater than or equal to 6. Benzene is the first member and of course the parent compound of all benzenoids, so it becomes essential. The molecular formula is C6H6. It is unsaturated nature. So unsaturated, it has an unsaturated nature. In presence of sunlight, benzene adds 6 chlorine atoms to form hexachlorobenzene. Similarly, benzene can form triozonoid structure. Benzene can be catalytically hydrogenated to cyclohexane. All the above reactions indicate that benzene has 3 double bonds and 1 triple bond and a double bond. So in this way, the different structures for the benzene are given. Different structure for the benzene are given. And the possible structure is the Kekulé structure. And the possible structure, and finally it was given by Kekulé. Now, whatever may be the structure, now let us see the benzene, how it undergoes the electrophilic substitutions. We know the molecular orbital theory. It is having the delocalization of the double bonds. It is rich in pi electrons. It is aromatic in nature. It undergoes substitutions rather than additions. It follows Huckel's rules. It undergoes aromatic substitutions. That is, electrophilic substitutions are more favorable. The replacement of an atom, generally that is hydrogen or a group attached to the carbon of the benzene ring by another group, is known as aromatic substitution reaction. Like the substitution aliphatic system, aromatic compounds may be substituted by 3 mechanisms: electrophilic substitution, nucleophilic substitution, free radical substitution. They involve the attack by the electrophile or electron-seeking reagent. Now, the substitutions involving attack of the nucleophile or electron-donating reagent. Free radical substitution, they involve attack by a free radical, is a free radical substitution. Unlike the aliphatic systems, Electrophilic substitution reactions are most common in aromatic compounds. It is most common in aromatic compounds. Next, aromatic compounds. Here, the electrophilic substitutions are common in the aromatic compounds, and all the common and well-known substitution reactions are nitration, halogenation, sulfonation, Friedel-Crafts reaction, that is alkylation and acylation are examples of electrophilic substitutions. Now, I'm going to discuss why aromatic compounds undergo electrophilic substitutions. Here, due to presence of pi electron cloud above and below plane of the benzene, due to presence of the pi electron clouds above and below the plane of the benzene ring or any other aromatic ring, the ring serves as a source of electron and it is easily attacked by the electrophiles, electron loving reagents. Hence the electrophilic substitution reactions are the characteristic reactions of aromatic compounds. Now, the electrophilic aromatic substitutions proceed by a common mechanism. Specific substitution reactions like nitration, halogenation. The common mechanism for these, both the alkenes, benzene, susceptible to the electrophilic attack, and both form carbonium ions as intermediate. But the carbonium ion produced by alkene combines with nucleophile to form addition product. If this has to happen with benzene, it will no longer retain its aromaticity. Therefore, it loses the proton to the nucleophile and regenerates the aromatic system of the benzene. Now, the following are the electrophilic substitutions: nitration, halogenation, alkylation, Friedel-Crafts alkylation, Friedel-Crafts acylation, and sulfonation. I'm going to give you a brief view of the mechanism. Then I'm going to give you the examples. Electrophilic aromatic substitution reactions are believed to proceed by molecular SE2 mechanism. It involves three steps. First one is generation of electrophile reagent. First of all, electrophile says the X plus is generated from the reagent. Electrophile is generated from the reagent. The second step is formation of intermediate carbonium ion. Benzene undergoes electromeric effect with the result of one carbon of the benzene ring, and it gets positively charged and other gets the negatively charged. The electrophile then attaches to the negative center, resulting in the formation of intermediate known as aronium or the carbonium cation. It is a sigma complex. And the sigma complex, the carbonium ion, it gets stabilized by the resonance structures. Different resonance structures are formed, and thus the positive charge of the intermediate carbonium ion is confined to one carbon, and thereby the formation of intermediate carbon is a slow step. It is a rate determining step for the complete reaction. And the third step is the formation of the product. Third step is the formation of the product. The reaction is completed by abstracting proton from the carbon atom, which is bearing electrophile by anionic species present in the reaction mixture. to form substituted product. And next, let us apply this general mechanism on nitration, halogenation, sulfonation, Friedel-Crepes alkylation, Friedel-Crepes acylation. Nitration, we'll see. Benzene, when reacted with a mixture of nitric acid and sulfuric acid, it gives nitrobenzene. The nitronium ion acts as the electrophile. It is generated from nitric acid and sulfuric acid. This nitronium ion attacks the electron-rich benzene to give carbocation as the benzenonium ion. The last step is the loss of proton to give nitrobenzene. The last step is the loss of proton to give nitrobenzene. You can see benzene in presence of sulfuric acid and nitric acid. It forms nitrobenzene. Here the mechanism, it undergoes 3 steps. Nitration is brought about by treating aromatic compound with the nitrating mixture. Nitration is brought about by treating this aromatic benzene with nitrating mixture, concentrated nitric acid and sulfuric acid. And the 3 steps involved are generation of the electrophile. Next, second one is formation of carbonium ion. The third one is formation of final product, nitrobenzene. Yeah, benzene is getting nitrated. Now we'll see the mechanism stepwise. Step 1 mechanism. Nitric acid and sulfuric acid. This is the nitrating mixture, reacts to give the electrophile, nitronium ion and H3O plus ion and 2 HSO4 minus ion. This nitronium ion is the electrophile. Nitronium ion is the active nitrating agent, electrophile. It is produced by reaction of nitric acid and sulfuric acid. HO and bond NO2 plus H2SO4 gives rise to H3O plus NO2 plus HSO4 minus. Here you have to note that sulfuric acid acts as an acid and protonates the nitric acid. It acts as the base, which is formed protonated nitric acid. This one, it is later getting decomposed into nitronium ion and water. Nitronium ion and water. Water so formed is absorbed by another molecule of sulfuric acid. Formation of the carbonium ion, we'll see. The step 2 is formation of the carbonium ion. When this electrophile, nitronium ion, attacks the benzene, the pi electrons, whatever the pi electrons are there, they shift towards this carbon. The carbon gets the negative charge and this carbon gets the positive charge. Wherever the negative charge is attained, it is attacked by the nucleophile. You can see with this carbon, the nucleophile is attached. And one thing you have to remember is all the carbons are same. The priority of all the carbons is same. It can attack anywhere, and that will be the carbon 1. And the next group will be decided by the first group. That is the orientation. Here, as the electrophile nitronium ion attacks, the carbocation is formed. Now, step 3 we will see. But here there is resonance structure. There is resonance structure. Once the carbonium ion is formed, this carbonium ion, the positive charge, it here the electrons are shifted to this carbon. Here you get this here. The pi electrons shifts towards this carbon. Here it gets minus charge, minus plus you'll get the double bond, and the carbocation, the carbon positive charge shifts to the bottom. And the same, again, the pi electrons shift towards the back carbon. So here the negative charge is obtained. Positive plus negative, you get the bond here. And this carbon will attain the positive charge. Finally, the H plus ion, the electrons are shifted to this carbon and the bond is formed here. And it's getting stabilized. This way the H plus ion is left. So what I mean to tell is the nitronium ion attacks this carbon. And here you're getting positive charge. This positive charge, formation of this carbocation, positive charge, shifts toward all of the ring. Electrophile, it undergoes electromeric effect. One carbon atom of the benzene undergoes positive charge and others get the negative charge. The electrophile then attaches the negative center, resulting in the formation of aronium carbonium cation. Sigma complex is formed. So it is getting stabilized by the resonance structures. Different resonance structures will be formed here. I didn't give you the complete detailed one, but different resonance structures, 1, 2, 3, 4 are formed. Resonance hybrid you call. So the positive charge of the intermediate carbonium ion is not confined to one carbon, it is dispersed entire molecule ring in the ortho-para positions. And thereby the carbonium ion is stabilized. The carbonium ion is stabilized. And whatever carbonium ion is stabilized, now it will go on give the final product. The step 3. We can see here the final step 3. In the step 3, as I've told you, the positive charge just shifted to all the carbon atoms, and at one place you get the carbonium ion. With this H plus ion gives out the electron to this carbon and it leaves as the H plus ion. So the final product is nitrobenzene is formed. The reaction, it is completed by abstraction of the proton from the carbon atom bearing electrophile by an anionic species. By an anionic species. So the formation of the product we can see. That is the substituted product nitrobenzene is formed. Now we'll see the second substitution, that is halogenation reaction. Benzene, when reacted with chlorine in presence of ferric chloride, it forms chlorobenzene. In the chlorination reaction, ferric chloride combines with chlorine to yield the complex which acts as the better electrophile. So, in the mechanism of the halogenation, again the steps are the same. First, the electrophile is generated. First step. The second step is intermediate carbonium ion is formed. And the third step is product is formed. Third step is product is formed. First one, in the mechanism of halogenation, aromatic halogenation, chlorination and bromination, It is brought about by treating aromatic compound with halogen in cold, dark, and in presence of strong Lewis acids such as ferric halide or aluminum halide. The usual practice is to add the reaction mixture aromatic compound plus halogen. Some of the iron fillings they convert by the halogen into the corresponding ferric halide. So the common three steps of the reaction are below. First one is the electrophile formation. The metallic halide Lewis acid polarizes halogen molecule to yield electrophile. X plus halonium ion is the electrophile. For example, if you see FeCl3 and Cl2, FeCl4 minus and Cl plus is formed. Cl plus chloronium ion is the electrophile. Next, coming to the next reaction, we'll see aromatic halogenation, chlorination and bromination can be carried out by treating aromatic compound with the halogen in presence of strong Lewis acids such as ferric chloride or aluminum halide. The usual practice is to add the reaction mixture plus halogen. The three steps: the metallic halide Lewis acid polarizes the halogen molecule and yields the electrophile halonium ion. FeCl3 plus Cl2 gives rise to FeCl4 minus plus Cl plus ion. The second step is formation of the carbonium ion, and the next one is the formation of the final product. Benzene reacts with the chlorine in presence of FeCl3 to form chlorobenzene. In chlorination reaction, ferric chloride combines with chlorine to yield complex which acts as the better electrophile. And the next step is from this complex, only chlorine is transferred without its pair of electrons to benzene to form carbocation. Loss of the proton in the final step yields chlorobenzene. Yes, this is benzene. It reacts with Cl2 in presence of FeCl3 and it gives Cl, chlorobenzene. Now we'll see stepwise. First step, chlorine. It is reacting with this Lewis acid catalyst. FeCl4 minus is formed and chloronium electrophile is formed. And the second step is carbonium ion formation. This is the second step. Benzene on reaction with this chloronium ion, it forms chlorobenzene and the carbocation is formed. As this chloronium ion is approaching, the pi electrons are shifting towards a carbon where it gets the negative charge and the positive chloronium ion attacks at the negative carbon. Thereby, here the chlorine is attached and you get the carbocation. And in the carbocation, the pi electron shift here and the positive charge is shifted to the para position. That is second resonance structure. And the third one is, again these electrons shift towards the back carbon and the positive charge is shifted to the ortho position. So from ortho position, para position, ortho position again, the carbocation, the plus charge is shifting the whole ring. So the resonance hybrid is formed and due to this resonance, the benzene is getting stabilized. You get different structures. And this carbocation, whatever is formed, that is a sigma complex, Finally, it reacts with FeCl4 minus to give chlorobenzene, and again the catalyst is back. In a similar fashion, we can do bromination. Step 1. Bromine itself is less reactive towards benzene. FeBr3 makes bromine more electrophilic by polarizing it to a complex. And in step 2, take up the electrophile complex on the benzene and formation of the bromine benzene in the third step with the loss of proton. You can see the steps. Once if it is chlorination, you have to take FeCl3. If it is bromination, you have to take FeBr3. With respect to the halogen, you have to select the catalyst. Here, again, the step 1 is the same for bromination as well as the chlorination. Bromonium cation is formed and FeBr minus is formed. It completely attacks on the benzene, carbocation is formed. This carbocation positive charge shifts from ortho to para, para to ortho. It's completely moving in the ring. It's completely moving in the ring. Thereby from ortho, para and ortho, the positive charge is shifted. Okay, so this is the way the carbocation gets stabilized by the resonance structures. And in step 3, you see in the step 3, the carbocation, whatever is formed, the H plus ion loses its electron, it gives its electron to the carbocation, and H is left in play as of H plus ion, and the carbonium ion is, the positive charge is lost on the benzene, and bromobenzene is formed. The final product, bromobenzene, is formed. Since the reactions between benzene and fluorine is very vigorous, fluorination is not possible. And hydroiodic, it is a strong reducing agent, it will reduce iodobenzene. So formation of iodobenzene to benzene back, iodination should be carried out in presence of oxidizing agent like iodic acid, nitric acid, and mercuric acid. So halogenation of homologous of benzene, it undergoes different types of halogenations, that is chlorination or bromination. Fluorine, it is vigorous. So the bromination, it can be achieved in the dark, cold, in presence of halogen carrier. On the other hand, side chain chlorination, bromination can be favored at high temperatures. At high temperatures, this can be favored, side chain chlorination, bromination, in presence of light and halogen carrier. Thus, when chlorine is passed through toluene solution, presence of sunlight, substitution takes place at side chain. Okay, so we have to remember that nuclear halogenation takes place through ionic mechanism, while side chain substitution takes place through free radical mechanism. Nuclear halogenation takes place with ionic mechanism, plus and minus formation. Whereas ionic mechanism, it takes place through the side chain substitution free radical mechanism. So these are the two electrophilic substitution reactions. Two electrophilic substitution reactions which we have discussed in today's class. Okay, one is the nitration, benzene nitration. The second one is the fluorination. So whatever it is, the 5 electrophilic substitutions are nitration, halogenation, alkylation, Friedel-Crafts alkylation, Friedel-Crafts acylation, and sulfonation. All these mechanisms follow in a general way, that is, first step is electrophile formation, the second step is carbocation formation, and the fourth step is carbocation is stabilized by the resonance, 4 structures. And the fifth one is, and the fifth step is the final product formation. So I have discussed about the nitration, nitrobenzene formation, and halogenation reaction. In this halogenation, we have seen about the chlorination and bromination halogenations, where the fluorination and iodation are possible, and how a side chain halogenation and the ring halogenation takes place also. I've discussed. Ionic mechanism is there for the nuclear halogenation, and free radical substitution is there for the side chain substitution. Okay, I hope everybody have understood today's class of the ESR reactions in benzene, electrophilic substitution reactions in benzene. I've discussed two reactions. And tomorrow's class, I'm going to discuss in detail about the sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. Thank you, everybody.